You've got a quadratic graph here, an x squared graph. That's a parabola. And that's a linear equation. So when they cross, they would cross in two places. So you should have two solutions there. Kind of got to just kind of think out of the box there, as to what you really have. Okay. All right, let's look at another one. X squared plus y squared equals 13, and x squared minus y squared equals 7. And the video doesn't seem to be wanting to stick around today. Yeah. So we may have to just not have a video today. I've got another recording of this same lecture, so I'll post a link to it to you guys, so it shouldn't be a big deal. This one, you got squared on the x's, squared on the y's, and so this one is one of those obvious elimination ones, because look at the y squareds. You got a positive y squared, you got a negative y squared. This is one of those where instead of going to my substitution idea, I'm like, oh, I've got an obvious elimination there with the y squareds, that if I add these two equations together, the y squareds are going to cancel out. And I'm going to get 2x squared equals 20. And I can solve that pretty easily. Divide by 2. X squared is equal to 10. Square root, plus or minus on that side. Plus or minus the square root of 10 are the solutions for x. So pick one of the equations to plug into. They both have the y squared in there, so it's not going to change, how many answers you get out of that. So if I'm just going to go to the top one because it doesn't have any negatives in it, and I plug in the square root of 10 and solve that. When I square the square root of 10, that's 10. Subtract 10. Y squared is equal to 3. Take the square root of both sides. So for that positive square root of 10, I get positive square root of 3, and I get the negative square root of 3. All from the positive square root of 10. So there's two of my answers. If I plug in the negative square root of 10, so I can go back to the same place. When I square the negative square root of 10, it still turns into positive 10. So I get the same two answers for that, the negative square root of 10. I get positive square root of 3 and negative square root of 10 gets negative square root of 3 as well. So I get 4 solutions out of that. Reason I would get 4 there is I have 2 circles that are intersecting one another, is what those equations are. They're equations of circles. So they could intersect it at 4 different places there. All right. Look at another one. Fun stuff. X squared minus y squared equals 4. I lied to you. Those are not two circles. It's one circle and one hyperbola, if you've done conic sections before. Hyperbola looks like that when you graph it. And if you graph a circle around that, it's kind of like the seams of a baseball or a tennis ball. That's how that works. But not exactly how that works. Let's do x squared there instead of x cubed. X squared minus y squared equals 4. All right, so this one, not an obvious elimination that can happen. You've got y by itself in one of the equations, but it would seem like you would what we've done in the past in algebra classes, if y is by itself, you replace whatever y is with what y is equal to. But with nonlinear systems, sometimes you think of it the other way around. You're like, y is equal to x squared. So that means, I can take this stuff, what x squared, and replace it with what x squared is equal to. If x squared is equal to y, I could replace x squared with y. With nonlinear systems, you got to kind of think a little differently sometimes. So that would give us an equation y minus y squared is equal to 4. And that's a quadratic equation. So I can solve that by getting it equal to 0 and getting it in the right order. And then I'm just going to change the sign of everybody because that makes it easier. And then solve it. So if I use my quadratic formula there, it's y equals this time negative b plus or minus the square root of b squared minus 4 times a times c over 2 times a. That's going to be 1 plus or minus the square root. That's 1 minus 16. 1 minus 16 is negative 15. What kind of solutions? Yeah, complex with imaginary in there. If that's the case, since we're dealing with systems of equations, the difference in solving a regular equation and a system of equations is with systems of equations, you're looking for where things cross. If they cross at a complex number, it's not going to show up on the graph. So we stop right there because this is complex. We just say it's no real solutions. We don't even find the other half of it. If it turns into a complex solution at any point, so there may be you might actually find a real x value, but if the y values are complex, then that means they're not real solutions. They would not show up on the graph. Okay. All right. The granddaddy of them all here. The last one. It's a toughie. 3xy minus 2y squared equals negative 2. 9x squared plus 4y squared equals 10. All right. This is a very strange one because you have that piece right there. That's the weird thing. The xy term. Okay. Anytime you have an xy term in there, it makes things a little bit more difficult. Makes it harder to work with a problem. So you've got to do almost like a double substitution type thing to get things to work. And anytime I want to have to substitute a little more than normal, a lot of times, there's usually some sort of elimination that could happen that would shorten it up just a little bit. This is still a long problem no matter which way you do it. Okay. So when I look at this problem, I see an obvious elimination that can happen with the y squareds. I got a negative 2y squared on top, and the bottom one has a 4y squared. You could easily turn the top one into a negative 4y squared by doing what? Yeah, multiply that entire equation by 2. Because you do it to the whole equation, it doesn't hurt anything. It's legal to do that. So that'd give us 6xy minus 4y squared equals negative 4. And then the second equation, I'm not changing at all. Okay. And then when I add those two together, the y squareds go away, so that I've got this equation that's not really pretty, but it is just one equation now. And I'm looking at that and I'm thinking, okay, maybe I could simplify that a little bit. 9 and 6 and 6 are all divisible by 3. So I'm just going to divide everybody by 3 just to make the numbers smaller. Okay. Now, since I have this equation and it has the xy piece in it, I think I should probably do my best to not have that term hanging around, because I can solve things that have just an x variable in it. I can solve things that just have a y variable in it. Things that have x and y at the same time, borderline impossible to solve. So I can get this equation to equal y by just isolating y like I normally would with an equation. I could subtract the 3x squared. And that's going to give us 2xy equals 2 minus 3x squared. And then to get y by itself, I could divide by 2x. And that's kind of crafty to do that. But by being crafty, I've got to put this stipulation in here that x cannot be what number? What's the only number that would mess up the denominator here? 0. Remember, we never can divide by 0. So if we divide by that variable there, mathematically it's legal as long as that variable is not 0. If it turns out where x was equal to 0 when we get done with this problem, then we've got to start over and try something else. It doesn't turn out to where that's what's happening. Okay, but we've got to make sure we state that at some place there, that x can't be 0. All right, then I can take that problem and say, okay, well, I've got y is equal to something. If I go back and look at my original problems, that second equation has an x and a y in it, and that y doesn't have another x on it like the first equation. The first equation's got this term in it. We've already seen that kind of messes things up, makes it pretty difficult. But this equation has got x squared and it's got y squared. I know what y is. I've got this thing boxed in down here that tells me what y really is equal to. I can put that in the place of that y squared. And then I have a problem that only has x's in it. It's not a pretty problem. It's not an easy problem, but it is a problem that only has x's in it. So that's what I'm going to do. I'm going to take 9x squared plus 4, and then I'm going to replace this y squared with that stuff. Okay? So that's 2 minus 3x squared over 2x squared. And that's equal to 10, supposedly. Okay. Well, order of operations tells me that I have to square this fraction first before I do anything else. So do that, 9x squared plus 4 parentheses, and if the bottom part's the easy one, that's 4x squared. And then the top part, if I square 2 minus 3x squared, that's going to be 4. 3x squared times 2 would be negative 6x squared, so that's negative 12x squared plus 9x to the 4th. That's still equal to 10. I've just squared that fraction. That's all I've done there. And then I need to distribute the 4, but I can kind of save myself a little work here. This 4 and this 4 would cancel each other out, so I don't have to distribute those. So that helps a little bit. 9x squared plus 4 minus 12x squared. Oh, let me put that in the right order. 9x to the 4th minus 12x squared plus 4. All that's still over x squared. Now, like I said, not an easy problem, but it only has one variable. So it's more doable than the one that had 2 variables in it, right? So got to remember some stuff about rational expressions and rational equations. In order to solve them, you got to have the same denominator. So I'm going to fix the 2 pieces that don't have a denominator of x squared. They have a denominator of 1 currently. They need an x squared down there. So if there's a 1 there, to turn it into an x squared, I multiply by x squared. But I got to do that to the top as well. So that gets us 9x to the 4th plus 9x to the 4th minus 12x squared plus 4 over x squared is equal to 10x squared over x squared. Once I get the denominators the same, I can drop them and then just do the numerator equation, which is still not an easy one, but it's doable. I got 18x to the 4th minus 12x squared plus 4 equals 10x squared. In order to solve that, I need to get it equal to what? 0. So I'm going to subtract 10x squared. That's 18x to the 4th minus 22x squared plus 4 is equal to 0. Could I make that a little easier on myself? Make the numbers smaller. 18, 22, and 4, all divisible by 2. So I'm just going to divide everybody by 2. That's 9x to the 4th minus 11x squared plus 2 equals 0. Okay. Now, I've got a trinomial, 3 terms. It's not quadratic. It's an x to the 4th power. So I've got a polynomial that I could work on solving. A couple of different ways to do that. One way would be do that rational zeros theorem thing with the p over q and graph it, see where it crosses the x-axis, and see if that could get us some answers. Or another way is, because it has 3 terms, I could try to factor it using the x method that we used way back when. Multiply to be 18, add to be negative 11, negative 9, and negative 2 does that. So that's the kind of the ticket out of this one, is that. So that'd be 9x to the 4th minus 9x squared minus 2x squared plus 2. And you group 9x squared. And then that leaves not 9, but x squared minus 1 minus 2. That leaves x squared minus 1. So my factors are then x squared minus 1 and nine x squared minus 2. And I set each of those factors equal to 0 and solve them. This one doesn't turn out to be no solution because x squared equals 1. I take the square root of both sides. X is equal to plus or minus 1. 2 answers. Solving this one. Divide by 9. X squared equals 2/9. Take the square root of both sides. I end up with plus or minus square root of 2 over the square root of 9, which the square root of 9 is 3. So far, I've got x solutions of positive 1, negative 1, positive square root of 2 over 3, and negative square root of 2 over 3. None of those are 0. So that tells me, hey, this worked. Now all I have to do is find the y values that go with those. So I take each one of those, and I'm lucky enough that I did the work to have this equation that said y equals negative 3x squared plus 2 over 2x. That's from way up here. I wrote it in a different order. But that thing right there, that says y equals that. All I got to do is plug in each x value and work it out, and I got the y value that goes with it. Okay. This is where I would employ the old calculator, save myself just a little bit of work here. And I would, in my graphing calculator, I'd type in negative 3x squared plus 2, and then close the parentheses, divided by, and then parentheses 2x. And then I'd go to my trusty table here, second graph, and I would type in negative 1, and I get 1/2, 0.5. If I plug in positive 1, I get negative 1/2. So for negative 1, I get 1/2. For positive 1, I get negative 1/2. Shuffle over in here. For square root of 2 over 3, second square root 2, whoops, not times, but divided by 3. I'm just going to use the decimal approximation for that, 1.4172. And then the negative square root of 2 over 3, negative square root of 2 over 3, negative, I don't want to put 72, that's just a 2 there. There we go. Wait, no, it wasn't. It was a 4, 2, that's what it was. There was a number there. And that's just the negative side of that, 1.4143. And those are the solutions for that system. That is as tough as they get, guys. They are definitely very difficult. I've never seen them in 6 years of teaching 140 put one of those on the final, and I generally don't put one of those on the test. Okay, so I'm obligated to show it to you. I've done my job. Okay, so perseverance is the key to those types of problems. Okay, so let's push through and go on and get to section 12.7, which is a much easier section. And then 12.8, it's also easy. I'm going to swap to some graph paper here because we're going to graph a few things by hand, actually. I hardly ever do anymore, but not the college level anyway, but I need to do that. 12.7, systems of inequalities. Systems of inequalities have way more answers than systems of equations do because it's the overlapping of all the solutions for 2 different inequalities, 3 different inequalities, heck, 7 different inequalities. It doesn't really matter how many that throw in together. It's the overlapping that the solution comes through. So just a quick review here. Let's throw a couple of linear ones together. Y is greater than 3x minus 7, and y is less than or equal to let's do negative 2/3 x plus 5. Okay. So, myself a ruler here. We're just going to graph those on the coordinate plane. Y-axis. Sure, we got plenty of room on the x. Oh, the positive and negative side of things. All right, so the top one there, y-intercept's -7. So 1, 2, 3, 4, 5, 6, 7. Up 3 over 1, up 3 over 1, up 3 over 1. Slope-intercept form is what that is. Now, the difference in graphing goes to the inequality symbol. Once you've plotted the y-intercept and gotten the slope a few points there, you look at the inequality symbol. If it has the equal to mark, the line is solid. If it doesn't have it, the line will be dotted. So this one would be a dotted line for the first one. So I'm doing that one in red. So this one is a dotted or dashed line, depending on how you were raised. Dotted or dashed. The second one, and now before we even go any further, we can do the shading on that one. It says y is greater than that. That should be above that line, but as that line gets closer and closer to vertical, it's harder to tell what's above or below. The kind of the fail-safe way of shading those is to put a test point in on one side of the line. If it's true, shade the side the test point's on. If it's false, shade the other side. And I can pick a test point pretty easily there. 0, 0 is a really easy one to test if the line doesn't go through it. If the line goes through it, you can't use that point. So if I plug that in here, is 0 greater than 3 times 0 minus 7? Yes. So this side would be true. So my shading would occur above that one, which is to the left of that. So shading above. And then I'm going to go and graph the second one. I'm going to graph it with a blue line. The y-intercept would be 5. 1, 2, 3, 4, 5. And the slope is down to right 3. Down to right 3. I'll do that one more time. And it would be a solid line because it has the equal to mark. Okay. And then shading for that one, if I tested the 0, 0 point again, it should be less than, so we're thinking below. Just checking to make sure 0 less than or equal to negative 2/3 times 0 plus 5. Is 0 less than 5? Yes, that's true. So I would shade below that line. And the solution is the green part there, the overlapping of those colors. So this is your solution area for that problem. Overlapping there. With the graphing calculator, you can do that as well. You can get 3x minus 7. And then you arrow over to the left of where it says y1. And if you got a newer one, you press enter and it's going to come up and you get to go through a menu system to change. And that would be the shifting above. If you've got one of the older ones, the non-color ones, you just press enter until it changes that picture to the triangle above. And okay, so I've typed in my equation that I want it to graph. Then I just press to the left until I get over here to the left of where it says y1, and then just press enter, and it'll change that picture beside of it from a straight line to the various options that you have. And we show the graph for that one. We see that same shading that we did with the graphing calculator. Okay. And then I'm going to put the other one in Y2, which was, what was it? I don't even know what I made it up. So negative 2/3 x plus 5. So negative 2/3 x plus 5. And then I'm going to press to the left until I get to that one, and it's a less than or equal to. So I want the triangle below. And then, okay. And then hit graph, and we see that same picture. And there we have our overlap here in our graph. Which it mixes the colors pretty good, makes a nice little purple with the blue and red. Any art majors there. So you may not have ever done that with the graphing calculator. There is an app that does inequalities. The only problem with that app is it's not really legal for you to use it in Math 140. So I don't show how to use it. And it also messes up the graphs when you go to do polynomials later on, that it just throws errors into the graphing of regular polynomials. And it's just a buggy little... The inequalities app on the calculator, it messes up graphing some other things. I'm talking about an app on the calculator, like this button here that says apps. There's one called Inequals, and it allows you to put in the actual inequality symbol there. But it, like I said, it throws errors kind of like all over the place when you try to graph some other things like normal graphs that are not inequalities. It throws some errors on that, which makes it pointless to me. I mean, if you're going to put a program out for that thing, make sure it works on everything. It's not just all that stuff. So most of the time, if I have students in the high school classes that have trouble graphing a polynomial, they've got that Inequals app running, and it's causing problems. So when you start to do the Inequals app with polynomials, like the next example, they have a lot of trouble then. That's why I don't use that app at all. That, and why would you? It's too easy to do without it. X squared minus 4, and y is greater than or equal to that, and then x plus y is less than or equal to 2. So we have a quadratic and a linear one mixed together. They just kind of mix and match some stuff in this. The first one, the top one there is already ready to go, so I'm just going to go ahead and graph it. Y-intercept there, or the vertex is at 0, -4. And it's a quadratic, so I could plug in some x values on either side. If I plug in 1 squared minus 4 would be -3. That'd be there and there. If I plug in 2 squared is 4 minus 4 is 0. So I just get an idea of what's going on there. If I plug in 3, that's 9 minus 4 is 5. Should be there, and then it's reflected on the other side. That should be a solid line. So I'm going to draw that parabola there. Pretty good till I got shaky on the right-hand side. And then the shading, it says greater than, so that should be above it. That's really the inside of that parabola because it opens up. So the shading should be inside of this one. For that. And then we'll graph the other one. You could get it in slope-intercept form if you wanted to, just by moving the x 2 down 1/1 indefinitely. And it's a solid line as well. And less than, so it should be below that. Solutions, and then that overlap area in the middle there. The graphing calculator, same idea. Clear that. X squared minus 4, and then this one was -x plus 2. But the graphing for that one was it's less than, so yeah, I got the right triangle there. Hit graph. There's that one. There's that one. It's overlapped there. Pretty easy to do. The only thing with graphing the inequalities on your calculator, you've got to swap that back. So you just go to the left of that and arrow or hit enter if you're using one of the older ones, and change it back to a line and click OK. Because it's not, you're kind of just manipulating it to think you're graphing inequalities. You're really just graphing things and telling it to shade things a certain way. And now it's back to graphing just lines. It's kind of boring, but anyway, if you've done fancy stuff, it's pretty boring. All right, so systems of inequalities. They don't get too crazy with those. They definitely don't put in the XY term in the inequality stuff. Again, probably like one question of that stuff on the final exam. Not a ton of that stuff happening. All right, last section of the year. section 12.8. And I'll be honest with you, I don't do a ton with this section as far as asking you to really stretch yourself on linear programming. It is a nice application section if you want to go through the business applications of inequalities and how things work there. If any of you aspire to be an insurance agent and sell life insurance, they show some nice linear programming examples in the graphs and charts that they use for that sort of thing. It's impressive for a math major to see that kind of stuff at work because there's no other place in life you'll use it. So that's why I don't really spend a whole lot of time with this. So the example that I show with this is just kind of defining some things that you have what's called an objective equation. And that objective equation would be given to you based on the problem that's presented. And it might be I equals 0.02x plus 0.03y. X and Y are some sort of variables about your life and your health risk or something like that mixed together and plotted on a coordinate plane. And then there's some restrictions that happen. And these restrictions, or constraints as they're called, that's what the math term is, constraints. In general, they x is greater than or equal to 0 and y is greater than or equal to 0 are standard in the thing. Not always, but most of the time they are, because we're dealing with the real world, and there aren't a whole lot of negative numbers when you start looking at inequalities in the real world. Just doesn't happen. And then, so what will happen here is these constraints would be graphed on a coordinate plane. And then you would have some lines going in various directions. And let's see here. Try to draw it semi-closer, right? And the overlapping of all of these inequalities that are graphed would create this region that's the overlap. That's the solution region to all the constraints. And there would be these points where all of these corners exist. And you would have those ordered pairs. Like this is 15-0. This is 15-5. This is 25. And this is 25-0. Those ordered pairs that are the corners of that constraint box, which I'll give you, are the things that you're going to check with the objective equation. So you're taking those x and y values and plugging them into the objective equation and checking out what's going on. They may be asking you to maximize or minimize the objective equation. Maximize, you're looking for the highest answer. Minimize, you're looking for the lowest answer, depending on the situation or the word problem that they're presenting, what they're going to ask you to do. But you will have this graph drawn for you. You will have those ordered pairs given to you for my tests. You just plug them in. Yeah, it really is that easy. Yeah. Yeah, so maximum, we'll find both of them on this problem. The maximum and the minimum comes from plugging those in. So let's plug in 0.02 times 15 plus 0.03 times 0. Work that out, that number. Then do the next ordered pair, which is 15.5. 0.02, 15, 0.035. Get that answer. Do the next ordered pair, which was 25. I'm just going around clockwise around the shape there. Doesn't really matter what order you do things in. Get that number. And then 0.02 times 25 0.030. Go ahead. I've got these numbers already. I've done this problem. 0.55 and then 0.5. So the maximum would be at the ordered pair 25, and then the minimum would be at the ordered pair 15.5. And depending on what the variables X and Y are, one of them may be investing a certain amount into two different types of accounts. And if you've got a certain amount that you can invest, in each account, what's going to maximize your return on that. So there's various options there. Life insurance is an investment. That's what I'm told. As you get older, you'll realize yes, life insurance is an investment. Remember that. You'll hear it again, I promise. Not to offend anybody whose parents are insurance salesmen. They do a great service to the people. And I have life insurance. I bought it. I bit the hook. So that's part of it. But that's like one of the only applications I've ever seen in my lifetime where somebody's using actual graphs of inequalities in life, because I always have that question. Everybody always asks, when am I going to use this? Well, you're not, unless you're an insurance salesman, and then you might. So don't get to say that very much. But some problems you might want to look at for these sections, page 9, 10, 5 through 53, page 921, 23 through 52, or 51, sorry. And then page 927, 3 through 8. Not a whole lot of problems there on the linear programming stuff, but some good practice there. Okay, I'll have a Canvas quiz up for the last one of the semester shortly, and then next week, meet, take your test, turn the test in, go study for your final for the rest of the week, and email questions if you got them on the practice final that I'll have on. I'll post it on Canvas this week. If you want to start working on it already, you can, and start emailing questions, and I can put something out there for your betterment. All right, you guys have a great week, and 2 more class meetings. Savannah, you can still make it work by 5. You better hurry. You ain't gonna. You done been to work. You work there too. Fun times at the Mickey D's. I think they'll hire me. Oh my God. Famous last words. I think they'll hire me.
You don't understand how much she is there. They know what she wants as soon as she walks in the door.
That's not a good thing. Oh my gosh. Oh wow. Oh gosh, that's funny.
Whenever you're working out that problem with the X, Y in it,
about
halfway through, I had a partridge in a pear tree.
Yeah, it is pretty. That's a rough one. That is a very rough one. A very rough problem. Anyway.
Speaking of working at McDonald's, I gotta go there and find out this week's schedule.
All right. Well, good deal. Have a good week.
You too.
I'll see you Monday.